1,160 particle flux units. That is how far above its warning line the electron population in Earth's outer radiation belt climbed this weekend, and it was the second day in a row it crossed. These are the particles satellite operators call killer electrons, and they damage spacecraft from the inside out. But there is no G number for this, no color code, no scale of any kind. Every public space weather reading was 0 while it happened. Here's exactly what crossed that line, what it does to hardware, and when the damage actually shows up. On Sunday afternoon, at 5 minutes past 5 in the evening Universal Time, an instrument aboard a NOAA weather satellite parked in geostationary orbit recorded a number that almost nobody outside a small professional community will ever see. The spacecraft is GOES 19. The measurement is the flux of electrons carrying energies greater than 2 megaelectron volts, and the number it recorded was 1,160 particle flux units. The operational alert threshold for that measurement is 1,000. Sunday's peak was 16% above it. When that line was crossed, the Space Weather Prediction Center did what it is built to do. It issued an alert. The product code is ALTF3, serial number 3721, issued at 35 minutes past 3 in the afternoon Universal Time, recording the threshold crossing 1 minute earlier. And buried in the comment field of that alert is a second number that matters just as much as the first. The previous day's maximum had been 1,077 particle flux units. The threshold had been crossed on 2 consecutive days. That alert is the entire public notification. That is not an exaggeration or a rhetorical flourish. There was no G number attached to it. There was no S number. There was no R number. Nothing appeared on the color-coded NOAA space weather scales that news outlets reproduce every time a solar storm is headed our way, because this measurement does not have a scale. It has a threshold and a machine-generated bulletin addressed to the people who fly satellites for a living, and that is all. You need to understand what you're looking at here, because the shape of this story is unusual. Nothing broke. Nothing is reported broken right now. No satellite went dark. No service dropped. No operator has announced a loss. What happened on Sunday was that a hazard indicator went above its warning line for the second day running in a part of Earth's environment where the damage it causes does not arrive on the day the number goes up. And while that was happening, every single measurement the general public has ever shown was reading as close to nothing as it gets. Here is what yesterday looked like from the outside. The geomagnetic field was quiet. That is not our characterization. That is the verbatim summary line from the Space Weather Prediction Center. The observed planetary K-index, the standard 3-hour measure of geomagnetic disturbance, peaked at 2 over the preceding 24 hours. The threshold for a G1 minor geomagnetic storm, the weakest storm category that exists on the public scale, is 5. The forecast maximum through Wednesday was 3.67, still comfortably below G1. And the forecaster stated plainly that no G1 or greater storms were expected at all. Solar wind speed at 21 minutes past 1 in the afternoon, Universal Time, was 366 kilometers per second, down from roughly 550 the day before. The interplanetary magnetic field, the magnetic structure carried along inside that wind measured 5 nanotesla in total strength, with the BZ component sitting at plus 1 nanotesla, northward. That single detail matters more than its size suggests. When the BZ component points south, it connects to Earth's field and opens a door for solar wind energy to pour in. When it points north, the door is closed. It was closed. Auroral hemispheric power, a direct measure of how much energy is being dumped into the polar atmosphere, was 14 gigawatts in the north and 14 gigawatts in the south. Genuinely active conditions run around 50 gigawatts and above. Yesterday was running at roughly 28% of that. The proton flux, the particles that trigger radiation storm warnings for aviation and for astronauts, was sitting at background, 0.263 particle flux units, with a peak of 0.322 over 24 hours, and a 1% chance of even the weakest radiation storm through Wednesday. And the NOAA scales feed, the thing that actually gets published, the thing a news desk would check, R0, S0, G0, nothing on any of the three. By every metric the public has ever handed, yesterday was one of the quietest space weather days of the month. And out in the outer radiation belt, the particle population that has been implicated in more commercial satellite damage than any other single space weather phenomenon was running above its alert threshold for a second straight day. The hazard indicator and the hazard scales were pointing in opposite directions on the same calendar day. That contradiction is the entire story, and to understand why it exists, you have to understand what these particles actually are. Earth is wrapped in 2 donut-shaped regions of trapped charged particles called the Van Allen belts. discovered in 1958 by an instrument that James Van Allen flew aboard Explorer 1. The inner belt sits relatively close. The outer belt is the one that concerns us, and it is populated by electrons that have been accelerated to energies where they travel at a large fraction of the speed of light. Geostationary orbit. The ring at roughly 35,786 kilometers altitude, where a satellite circles Earth once per day and therefore appears to hang motionless over one spot on the surface, is where the majority of commercial communications satellites operate. And geostationary orbit sits inside, or right at the edge of, the outer radiation belt for much of the time. That is not a design flaw anyone can engineer around. It is a geometric fact about where the useful orbit is and where the particles are. The people who operate those satellites do not call these particles relativistic electrons in casual conversation. They call them killer electrons. That term appears in the technical literature. It is not marketing. What makes them dangerous is not that they are fast, exactly. It is what happens when something moving that fast hits a spacecraft. A slower charged particle, the kind that arrives constantly in the solar wind, stops at the outer surface. It deposits its charge on the skin of the satellite, where engineers have known how to deal with it since the 1970s. Conductive coatings, grounding straps, bleed paths. The charge accumulates on the outside and it gets equalized away. That process has a name, surface charging. It is a solved problem, or close to one. Relativistic electrons do not stop at the skin. They pass straight through the outer structure of the spacecraft and come to rest deep inside it, buried in whatever insulating material happens to be in their path. Circuit board substrates, the dielectric layers inside coaxial cables, potting compounds, the resins that hold components in place. These are materials specifically chosen because they do not conduct electricity, and that is exactly the problem. The charge arrives, it stops, and it has nowhere to go. This mechanism has its own name, internal charging, sometimes called deep dielectric charging or bulk charging. And it is a fundamentally different phenomenon from the surface charging engineers spent decades learning to handle. Picture the process over days rather than seconds, because that is the timescale it runs on. The flux goes up. Electrons stream into the spacecraft and stop inside its insulation. More arrive. The buried charge accumulates, and as it accumulates, an electric field builds inside a solid material that was never designed to hold one. Every insulating material has a breakdown strength, a field intensity above which it stops insulating and starts conducting violently. When the internal field crosses that line, the material fails. What follows is an internal electrostatic discharge. In physical terms, it is a miniature lightning bolt going off inside the satellite's own insulation, and it couples an electrical transient into whatever circuitry is nearby. The satellite then receives what is, from its own point of view, a completely valid command that nobody sent. A switch throws, a setting changes. A control loop reads a value that is not real and acts on it. And here's the detail that makes this hazard so difficult to see, so difficult to forecast, and so difficult to prove after the fact. The discharge does not have to happen while the flux is elevated. The charge builds during the enhancement. The breakdown can come afterward, days afterward, in some documented cases, weeks afterward. Think about what that does to the record. For a solar flare, cause and effect are locked together. The flare peaks, the radio blackout happens, the timestamps match, and you can draw a line between them. For internal charging, the cause is a slow accumulation over 1 to 3 weeks, and the effect is a single instantaneous failure that can happen on a day when the space environment is completely unremarkable. There is no moment to point at. There is no photograph. There is no aurora over the horizon to make the front page. That is a large part of why this hazard is undercovered, and it is not a conspiracy. Journalism needs a moment. Human attention needs a moment. This process does not supply one. The delay does something worse than making the story hard to tell. It makes the failures hard to attribute, and unattributed failures do not enter the statistics that would otherwise force this hazard into public view. Consider how a satellite anomaly actually gets investigated. A component behaves incorrectly. The operator pulls telemetry, works backward through the subsystem, and tries to identify what changed. If the space environment was violent on the day of the failure, space weather goes on the list of candidates immediately. If the space environment was calm on the day of the failure, and under the delayed breakdown model it very often will be, then space weather does not look like a candidate at all. The investigation concludes with a component fault of unknown origin, and the entry goes into a private database that nobody outside the company will ever read. That last part is worth being precise about, because it is where the legitimate criticism lives. Satellite operators are under no general obligation to publish anomaly telemetry. Failures are commercially sensitive. They affect insurance claims, they affect contract negotiations, they affect the market value of a fleet. So the public record of space weather-related satellite damage is not a complete accounting. It is the subset that became visible for other reasons. Because the failure was too large to hide, because a government spacecraft was involved, or because a researcher went digging years later. The alert that fired on Sunday exists precisely because a small community of engineers and scientists spent decades establishing that this particle population damages hardware. They fought to get a threshold defined. They did not get a public scale, and there is a mundane reason for that which we will come back to. But the threshold itself is a monument to a real, documented, expensive problem. And there is one more feature of Sunday's event that makes it a textbook case rather than an oddity. The enhancement was not caused by a flare. It was caused by a coronal hole high-speed stream, and the stream was already dying when the flux peaked. A coronal hole is a region on the sun where the magnetic field opens outward into space instead of looping back down. Solar wind escapes through that opening at elevated speed, 500, 600, 700 kilometers per second, against a background closer to 400. And when that fast stream reaches Earth, it buffets the magnetosphere, drives waves through the outer belt, and accelerates electrons already trapped there to relativistic energies. 2 of these stream events are formally cataloged in NASA's database in the days before Sunday. The first was logged at 11 minutes past 10 in the morning, Universal Time on Tuesday the 21st, detected across 4 separate instrument packages aboard 3 spacecraft, and tied to an interplanetary shock 6 minutes earlier. The second was logged at 10 in the evening, Universal Time on Wednesday the 22nd, detected across 3 spacecraft, and here's the part that makes this more than an inference. That stream is formally linked in NASA's own catalog to a relativistic electron event on Friday the 24th, 2 days later. The relationship is not something we are drawing on a chart. It is recorded as a linked pair in the database. So the sequence runs like this. A high-speed stream arrives around the 21st and 22nd. The outer belt starts loading. By Friday, there's a cataloged electron event. By Saturday, the flux is at 1,077. By Sunday afternoon, it is at 1,160. And by yesterday, the stream that started all of it had faded. Solar went down from roughly 550 kilometers per second to 366. The magnetosphere quiet, the aurora at 14 gigawatts, while the forecasters were still projecting high electron levels through the day, easing only to moderate today and tomorrow. The effect outlived the cause. That is characteristic. That is what these enhancements do. And it is the reason a satellite operator cannot simply watch the solar wind and assume that when the wind calms down, the risk has passed. None of this would carry much weight if the historical record were empty. It is not. In January of 1994, 2 Canadian communication satellites, Anik E1 and Anik E2, suffered failures of their momentum wheel control systems roughly 9 hours apart. Television and computer data transmission went down across Canada. Remote northern communities lost telephone service. Investigators eliminated every candidate except one. An electrostatic discharge had damaged a specific component in the speed control loop of the momentum wheel assemblies, causing the control circuitry to report a false full-speed signal and spin the wheel down to nothing. The failures occurred during a period of enhanced relativistic electron flux. Anik E1 came back within hours. Anik E2 was out of service for roughly 6 months and was ultimately recovered through a ground-based attitude control workaround, rather than any fix aboard the spacecraft. Researchers revisited the case in the peer-reviewed literature 18 years later. In January of 1997, a geostationary communications satellite called Telstar 401, carrying computer data, telephone traffic, and television programming, failed abruptly and completely. Scientists at NASA's Goddard Space Flight Center attributed the loss to geomagnetic activity from a solar storm 5 days earlier. The satellite's reported value was around $200 million. The American Geophysical Union covered it in its own publication under the headline, "Did Space Weather Knock Out Telstar Seismic Network?" An unusually blunt question for a scientific society, and a good measure of how live the uncertainty was. In the autumn of 2003, during the storms now known as the Halloween events, 3 large active regions produced 17 flares in 18 days, including the most intense flare ever recorded. NOAA's own retrospective documentation states that roughly 59% of deep space missions and satellites across all orbits experienced anomalies, and that the majority of satellites in low Earth orbit were temporarily lost, requiring several days of round-the-clock work to re-establish their positions. Japan's ADOS 2, also known as Midori 2, ended its mission that October when its solar power system failed. It was carrying a NASA instrument reported at around $150 million. Astronauts aboard the International Space Station moved into shielded areas. Airlines rerouted away from the poles. A power grid in Sweden tripped. And in April of 2010, a geostationary satellite called Galaxy 15 stopped responding to ground commands, while its transponders kept broadcasting. It drifted uncontrolled through the geostationary belt for more than 8 months with a live payload, threatening interference with every satellite it passed, and its operator performed 15 separate flyby procedures to manage the risk. The industry nickname for it was the zombie sat, and the operator concluded the cause was an electrostatic discharge that corrupted the satellite's onboard software. We have to be careful with that last one, and we are going to be. Outside researchers wrote the Galaxy 15 event up as a space weather case study, and the United States Geological Survey maintains a page connecting it to a magnetic disturbance on the same day. But the operator stated publicly that the upset had nothing to do with solar activity, and its position remains that the exact cause of the discharge may never be known. That is a real disagreement between a company that owned the hardware and a research community reading the environment around it, and we are not going to pretend it has been settled. There is one more case, and it is the strangest, because it is the only one where humans caused the particle environment deliberately. In July of 1962, the United States detonated a 1.4 megaton nuclear warhead roughly 400 kilometers above the Pacific Ocean in a test called Starfish Prime. Among its effects was an artificial belt of trapped electrons that persisted for something on the order of a decade, and, at its peak, was more intense than the natural belts. At least 7 satellites were disabled. Telstar 1, the spacecraft that had relayed the first live television across the Atlantic, worked normally until that November, when radiation from the artificial belt made its command channel behave erratically. On the 23rd of November, 1962, the command channel stopped answering. Britain's first satellite was damaged, so was Transit 4B. Roughly a third of everything then flying in low Earth orbit was affected. The point is not the bomb. The point is that this is the one occasion when humans increased the trapped electron population on purpose, and then watched what it did to spacecraft. A controlled experiment no one would be permitted to run today, and the clearest causal demonstration on record that trapped relativistic electrons, not flares, are what kill satellites over the medium term. Individual case studies establish that something can happen. Statistics establish how often. In 2015, 2 researchers at the Massachusetts Institute of Technology, Whitney Lohmeyer and Carrie Cahoy, published an analysis that did the second thing, and it is the single most important piece of work behind this story. They examined 26 failures of solid-state power amplifiers across 8 geostationary communication satellites over 16 years of operation. Solid-state power amplifiers are the components that boost a signal before it is beamed back to Earth. When one fails, the satellite is still alive, but a piece of what the operator sells stops working, which is precisely the kind of quiet, partial, commercially awkward failure that never makes a headline. 3 findings came out of that work, and each one reshapes how you should think about Sunday's number. The first is that most of the failures did not cluster at solar maximum when flare counts peak and space weather makes the news. They clustered during the declining phases of the solar cycle. The second is the timescale. The anomalies occurred at a rate higher than chance would predict when the accumulated electron fluence over the preceding 14 and 21 days was elevated. Not the peak flux on the day of the failure, the accumulated dose over the previous 2 to 3 weeks. The controlling variable was history, not weather. The third is that when the team modeled the amplifier subsystem directly, the electric field building inside the dielectric material of the radio frequency coaxial cables over those 14 and 21 day windows was high enough to cause dielectric breakdown. The mechanism, the time scale, and the counterintuitive timing all landed in one paper. Set that against another result from 2003, in which researchers analyzed how the outer belt responded to 276 geomagnetic storms across 11 years. Roughly half of those storms increased relativistic electron flux. About a quarter changed almost nothing. About a quarter actually decreased it. A geomagnetic storm is close to a coin flip as a predictor of whether the killer electron population goes up or down, which means the one public scale that does exist, the G scale, is a poor proxy for the hazard that has no scale at all. That declining phase finding deserves more attention than it usually gets, because right now the sun is in exactly that phase. The sunspot number for June of this year was 94.4. The 10.7 centimeter radio flux, the other standard activity index, was 138.21. Both are down. The 12-month trend is minus 20.2 compared with a year ago, and the monthly sequence has been sliding since it topped out at 133.7 in August of last year. The cycle is descending. Read casually, that says the danger is falling. The physics says something more complicated. At solar maximum, the dominant drivers of space weather are flares and coronal mass ejections. Sudden, dramatic, extremely well covered, and mostly transient in what they do to the radiation belts. As the cycle declines, large coronal holes take over as the dominant driver, and coronal holes have a property that flares do not. They persist for months and rotate with the sun, which means the same hole sweeps past Earth again roughly every 27 days, firing the same high-speed stream at the same target over and over. Recurring streams are extremely efficient at loading the outer belt, so the period when public attention to space weather naturally declines, because the flare count is falling and the headlines dry up, is plausibly the period when this particular hazard is at its most persistent. That is not speculation added on top of the data. It is what the amplifier study found, in the anomaly record, across 16 years of hardware. Look at what the sun actually did in the last 48 hours, and the point sharpens. There were two M-class flares, both from the same decaying active region, an M3.2 peaking on Sunday afternoon, with a Type 2 radio sweep indicating a shock front moving at 1,057 kilometers per second, and an M1.0 early yesterday morning with a shock at 622. Those are real events. The first one even produced a minor radio blackout, and the magnetosphere registered essentially nothing from either of them. The one measurable particle effect of that entire window was the electron flux, the one with no scale, no color code, and no headline. 3 things are worth tracking from here, and each one has a date attached. The first is Thursday. A coronal mass ejection associated with Sunday's M3.2 flare was first seen in spacecraft imagery about 40 minutes after the flare peaked, and preliminary modeling puts a possible arrival late on Thursday. If it arrives, it becomes a live test of that coin flip statistic on this specific belt configuration. Does the disturbance drive the electron flux higher, leave it flat, or scour the belt clean? Half the time it is the first, a quarter each for the others. Whichever way it goes is worth reporting, because that uncertainty is exactly what makes this hazard so hard to forecast. The second is the middle of August. If the coronal hole that produced this enhancement is a persistent structure, it should rotate back into an Earth-facing position around the 3rd week of August. If the electron flux crosses 1,000 particle flux units again on roughly that schedule, it confirms a recurrent stream pattern and tells us the outer belt is being loaded repeatedly by the same solar structure. That is a specific, checkable prediction with a date on it, and we will check it. The third is the quietest and the most consequential. If the 14 to 21-day accumulated fluence model is correct, the operationally significant window from this enhancement runs into roughly the 2nd and 3rd weeks of August. Any publicly reported anomaly on a geostationary satellite in that window becomes a data point. And the fact that most such anomalies are never publicly reported at all is itself the thing to keep watching. So here is where this leaves us. Every space weather hazard that can hurt a person has a public scale. Geomagnetic storms have G, radiation storms have S, radio blackouts have R. They get color codes, forecast probabilities, press coverage, photographs of green light over mountain range. The hazard implicated in more commercial satellite damage than any of them has a number, a threshold, and a machine-generated bulletin sent to a few hundred people who fly spacecraft for a living. The honest explanation for that is boring rather than sinister. The NOAA scales were built around effects that ordinary people and non-specialist infrastructure operators actually experience. Grids and aurora, radiation exposure in aviation, radio and navigation degradation. Internal charging affects a specialist audience that already receives a dedicated alert product. The absence of a public scale reflects who the hazard's audience is, not a decision to conceal it. But the observation still stands on its own, without any conspiracy attached. A category decision made decades ago is the reason a consequential hazard runs almost entirely outside public view. On Sunday, that number went above its line for the 2nd day running, while every public scale read 0. It will probably do it again in about 27 days, and if it causes a failure, that failure will most likely happen on some unremarkable afternoon weeks from now, and be logged as a component fault of unknown origin. We will be tracking the numbers, and we will tell you what they do.